All right, welcome back, everybody. So today we continue our longest chapter, namely on witness sets. And we'll be discussing the way witness sets interact with the parametrized situation. So what do I mean by that? Varieties have come in two forms to us. One is via their implicit equations. You write down a bunch of equations and a bunch of variables, and you ask for all of the substitution values for those variables, which make all the equations zero. The other way that varieties have shown up in the wild is via parametrizations. So you have some polynomial map, say of c to the m, and you map it to some c to the n. Okay, the image of that map, maybe it's a variety, maybe it's not. Okay, take it to the risky closure, take the smallest variety containing it. And then that's your variety. So we're really looking at parametrizations like this. X First, okay. So that's what a parameterized variety is like. Linear spaces, which have implicit equations given by your favorite format from linear algebra, are parametrized varieties. And you knew this back in linear algebra, because you're often asked to describe the solution set to linear equations as some vector plus the span of some other vectors. And you all remember the algorithms to do this. Great, and what does that mean? That means you can also represent L as the image of, let's say, L, where L is mapped from some C T to the M, C X to the N, where T1, Tm goes to transpose A to right, but this is a different, and that's a different thing. Okay. Point is here, it looks like the null space of A translated by B. And here it looks like the column space translated by B. Sorry, this is not translated, but it does look like a shift of the null space to A. This is the column space of A translated by B. This form you might think of as the implicit form. Sometimes it's called the extrinsic form. It's external because your coordinates x live in the ambient space of the linear space. Whereas this is sometimes called parametrized. Yeah. Or intrinsic. Oh. Intrinsic because here the coordinates for the linear space are t. you actually don't get coordinates on the ambient space that you're putting it into. From this. And that we can represent linear spaces in these two different ways is an enormous feature, because it allows us to compute witness sets in different ways. Okay, so far, we've only been talking about witness sets in the context of the extrinsic representation of a linear space. I've been saying, okay, you add a bunch of linear equations and then you solve this. Okay, but that is not always going to be the best way, numerically, mathematically, or otherwise, to represent witness sets. And so let me just, let's give an example. So let's take the sphere. And great, so the witness cover, the parameterized polynomial system you would have to solve to get a witness set for the sphere would be this. Okay, so we have introduced two new equations and no new variables, so that we've obtained a square system. Right. Get some extra parameters in there, whatever. We also write a linear space generically as the image of something that looks like, okay, we're in three variables, so A1, A2, A3 times T. Oh, what's the dimension of the linear space we need? We need a line, right? So here, think about this as saying, okay, well, X has to be A1 T plus B1. And of course, when I put equal signs here, I really mean write the polynomial down that wants to be 0 in order for this equality to happen. So minus that, yeah. Y is A2T plus B2, and Z is A3T plus B3. Okay. So this we were happy with. Kind of happy with, but this is silly. Okay, there's something silly about this. These equations have substitutions looking at you in the face, right? Wait, X is that? Oh, okay, I should replace X with that everywhere in my equations, right? And same with Y and same with Z. And these will all become 0, and this will become just a polynomial in T. This is really just a univariate polynomial. And you may or may not have a preference to solve one univariate polynomial instead of 4 polynomials in 4 variables. Maybe. Maybe there's a reason you don't like the other format. Maybe there's a reason you do. But you can significantly reduce the number of equations and variables you have if you're paying attention to, well, what dimension of linear space am I trying to intersect with? And can I parameterize this intersection? What makes this example so extreme is that the thing we wanted to compute a witness set for was a hypersurface. Okay, so when it's a hypersurface surface, you're intersecting with a line, right? And lines are parameterized by one variable. So you can just do the substitution and get a univariate polynomial system out. The opposite end of the spectrum is Not when you're a hypersurface, which has dimension as high as possible, but you're a curve, which has dimension as low as possible. Right? Well, besides being points, in which case you're not doing anything anyway. As soon as you're a curve, it's not in your interest to parameterize an n-1 dimensional hyperplane by n-1 new variables and do the substitutions on everything. Rather, you might want to just slice with one linear equation. And so if you have a curve, you only have to include one linear equation. So if you're really high dimensional, you might want to parameterize the thing you're intersecting with. If you're really low dimensional, you might want to stick with the implicit linear space form. And homotopy continuation.jl has functionality for dealing with both types of linear spaces. More generally, what's going on? C to the, let's see. You have a variety. Yeah. How about by M equations? You can think about the map, which sends an n tuple in the ambient space. This evaluates your polynomial system. Might even call this map path. That would be an appropriate thing to call this. And then what are you doing? You're interpreting X as the preimage of the all zeros vector. If you like your arrows, this is what a variety is. It's the fiber of zero of some polynomial map. Then you might have some linear space, which is parameterized here. That's our L. I guess also inside here, I mean inside CX, L, which is the image of L. You don't have to do photo, but might as well. And now what is the interpretation in terms of these arrows of L intersect X? Well, it's just the preimage of zero of what map? Well, the one that does L and then does L. Okay. Anything in the image of L is in the linear space. So being in this intersection, you get for free as long as you're in the image of L. To further be in the image of X, sorry, to further be in X, you would have to map that image point to zero. And that's what's going on here. Is that you're doing F composed with L, and you're asking when that's zero. But this is E of F. Okay. So if you like looking at equations and then noticing that substitutions are staring at you in the face, great. If you like seeing kind of the more bird's eye view of what's going on, it's this. And this doesn't just pertain, this interpreting intersections of parametrized varieties and implicitly defined varieties does not just pertain when the parameterization is a parameterization of a linear space. Like when you replace this L with a P, this would become P of T. This would be some Y. This would be some P. This becomes P. Becomes Y. This becomes P. So the story is totally true, not just when you're parameterizing some linear space, but when you're parameterizing some other variety. If you want to represent the intersection of the parameterized variety and the implicit variety, you do the composition. And that gives you the coordinates for the intersections in terms of the parameter values of the parameterized variety. Okay. Technical thing. I should write that. Because this variety lives in CT, right? So if I wanted to compute the solutions, I get it in the coordinates T. I don't get it in the coordinates of the space I'm actually caring about. If I really want this to be an equality, I would say x intersect y is D applied to that circ. So in other words, we have a sphere. We have a copy of CT. This maps to the ambient space. Endowing every point here with a t value here. So t equals -1. This corresponds to t equals -1. But x, y, z, it's really L of t. Okay? So if we solve this, we'll get these 2 points, T1 and T2. But these T1s and T2s are really T1s and T2s down here. To get them in the correct space we care about, we have to go here. Okay. We have already used this trick when discussing the lines contained in the cubic. Right. So when we talk about the 27 lines on a cubic surface, the way we cooked up those equations, we wrote down an implicit equation for a cubic. Then we wrote down what a parameterized line looks like. And then we did the composition, and we got a polynomial of degree 3 in one variable. And we wanted that to be identically 0 to indicate that the line was completely contained in the cubic. So we've already done this composition trick. Okay. And you should know about it. It will sometimes make problems which were previously intractable on a computer much, much simpler, like in this case of computing a witness set for items. Any questions? There are some warnings to be had about this process. Parameterizations may not be one-to-one. They may be several to one, or infinite to one. So I can draw and visualize this. Here's the circle. And I am going to parameterize the line x equals y in 3 different ways, one of which you like, and 2 of which you hate. Somebody tell me the way to parameterize this in the way I like. You got this. Parameterize x equals y. E comma t. Yeah. T goes to tt. No matter what happens, points in the image of that will have their x value equal to their y value. Very good. So that's c to c squared. I'll now give you a map from c squared to c squared, whose image is also that line. Eek. Yeah. So no matter, so if somebody gives me 1, 1 here, well, I don't know. The preimage of that would be s t minus 1 equals 0. It would be the perfect. So that's an infinite to 1 map. Eek, that's gonna maybe cause us problems. So in other words, when you're picking parameterizations, as long as you have the power to pick it well. Okay. Sometimes you don't. We'll deal with how to talk about how to deal with that in a moment. Okay, what else could happen? Well, okay, let's go back to the right dimension at least. And let's see if there's a map from c to c squared. That will screw things up. How about t squared, t squared? So here, if you pick a point in the image, like boar, you get 2 points in the image. So this is 2 to 1. Infinite to 1. We like this. Any questions? So there's a fact you should know. Really well, having to do with the geometry of the image of a map. And this is true for any function, but remember this for your whole mathematical life. One day you might thank me. The image of a map is the image of the projection from its graph. Of projection. Okay, so what I mean, great. So I have, I won't even do it as sets, right? So I got a map from a set S to a set T called F. Okay. So think S is some C to the M, T is some C to the N. You'd like? Well, I can look at its graph. And you know what its graph is. It's all S and T such that, well, say where this lives, S cross T, such that S is T. This lives in Oops, S cross T. I can project just onto the second coordinate. Right? I'm looking at all the t values which belong to something in its graph. In other words, all the t values that get hit by something. Okay. Does that make sense? The image of a map is the image of projection from its graph. Now I'm going to erase the general picture here. I'm going to stick in some of these pictures here. So I want you to think about what this diagram looks like for these three things. Okay, do it. Let's do this last one first. C is going to C squared via T maps to T squared T squared. Okay, so the graph of this is, oh, this is not too hard to write down. T comma T squared comma T squared. Scroll over all inputs, select all outputs, that's it. Oh, this is in 3 dimensions, so we can actually write this. So here's the input axis, and then these 2 axes will be the output axis. Okay. And so yeah, when T is there, we get oops, wrong way. Oh. Okay, so when T is 0, 0, it's this. When T is 1, 1, or here. The 2, we get 4, 4. Here. So that's the curve in 3-dimensional space, which is the graph. And then the projection is just the pancake map in 3 dimensions. You just slop everything on the ground. And what you get under that projection looks like it's just this ray, because we're looking at a real picture. Right? So what t values give us -1, -1, I, and -I, -I. Right? So the real t's go to this part of the line, the non-real t's go to that part of the line. Okay. But again, the problem is that this projection, if I look at any point here, I look at the fiber, it's 2 to 1 map. Okay. And so if I wanted to use this to compute the intersection points of a line in a circle, well, I would be doing t to the 4th plus t to the 4th minus 1 equals 0. So I'd be solving this, right? And I would get 4 solutions. Okay, so these would be my t-vals, which are solutions. But then I'd have to map those t-values into the space I actually like, the xy plane. And I do that via this map. And we have 2 of these going to the same one, and so 2 of these going to the same. That's the story. I can't draw the graph of this, it would look in 4 dimensions. So, but you can imagine ways to give a function where the graph actually, yeah. So the graph of that, if we restricted it to this space, it would look like this vertical plane over the red line. So you'd see the infinite to 1 map. So projections don't have to be 1 to 1 or finite to 1, they can be infinite to 1. Right. Any questions? This is a big punchline in numerical algebraic geometry in the world of computational algebraic geometry, is that understanding the image of a map from a symbolic point of view in terms of equations is super duper hard. Doing it via witness sets is super duper easy. And so this gives you access to some representation of some varieties that you can't get your hands on symbolically. So since the image of every map is the image of a projection, we're going to focus on projections. But before I do that, I have to convince you that the equations for the graph of the image of a map are easy to write down. So if I have some ct to the km is what I like for dimension, cx to the n. So this is some polynomial map. T maps to f1 of t to fn of t. And here t is of course an m tuple of complex numbers. And the graph, call this capital F, the graph of capital F, I can write down the implicit equations. X1 has to be f1 of t1 tn. X2 has to be f2 of t1 to tn. And xn has to be fn of t1. Equations for graphs of functions are easy. Equations for images of functions are hard. But the point is we have equations for the graph. And that is fantastic news. Because now if we want to get a witness set for the image, we'll see how to get a witness set for the graph and how to turn a witness set for a variety into a witness set for a projection of that variety. Quite easy. I'm going to do a shorthand for this to save up some word space. Okay, so now let's just focus on projections. Okay. I'm going to draw some curve in 3-dimensional space. And you imagine just kind of looking at this curve from the top. what I've drawn here is the nice case. It's pretty much 1-to-1. The exception is here. Here there's 2 points upstairs. Just like if you take a thread and turn it around, any intersection points you see while you look down, they have to go through more than one strand, more than one branch of the thread. Okay. So this we're super happy about. We like these projections. And there's projections like this. Like the one we've already seen. These we're okay with. And there's projections like this. And these will actually be okay with. Pretty much 1-to-1. Sum to 1. Some number to 1. Finite to 1. And then infinite to 1. Our goal is to represent this intersection in a way so that we can move it around. That's what all of our algorithms require. They require a linear slice, numerical approximations for the isolated intersection points, and the ability to move it around. Okay. But we don't know equations downstairs, so we can't get a witness set downstairs of the form, FLS. Because we don't know equations, and I've already promised you don't want to get your hands on them. Okay, but we do have these equations upstairs, and we could have some witness set upstairs. Okay, it's in, pops out, goes back. So how do I turn a witness set upstairs into a witness set downstairs? Well, look, if I want to compute these intersection points, that's the same thing as computing all the points upstairs that map down there. So I can actually just extend this line into a 2-plane upstairs. And this will intersect at some point, maybe another point, another point. Yeah. So if you want to get a representation of a linear section of the image of a map, center your focus on getting a witness set for its graph, and then tilting the witness set to be vertical with respect to the projection that you're doing. Okay. You won't be computing points down here. You'll be computing points up here. Right? So you'll get something like the equations upstairs, the linear space. So let's say this is x, y, and z. So we're projecting onto xy plane. So this is the equation for this line down here. It's also the equation for this hyperplane up here, right? So being vertical here means just z doesn't matter. Oh, that's encoded here. So this really is in C. And then P1, P2, and P3. which of course each look like P11, P12, P13, P21, P22, P23, P31, P32, P33. Now, how do I get the points downstairs? It's just these parts, right? So it's actually easy to write them down because they are just the first two coordinates of whatever's going on upstairs. We just have extra stuff upstairs. Make sense? Okay. Great, and indeed, if we want to move this slice downstairs, that's fine. We just move this as usual as equations upstairs. No problem. But we have to be concerned about this, right? So with this, what happens in the process is, okay, I slice downstairs. I'm slicing a line, I should just have 1 point. I interpret that slice as the equations for something in the graph, so everything becomes like this big vertical linear space. I get 2 intersection points upstairs. So I have 2 of them, but they both have the same first 2 values. Okay, that's also very easy to check on a computer. Right? You do the projection as usual, and then you push in some function that takes only the unique points up to some numerical tolerance. What about the cylinder? So the cylinder is not too bad of a situation either, as long as you know you're in that situation. So if you try to play this game with a cylinder, what happens? You're like, okay, cool, I want that. And I slice, I get 2 vertical lines. Okay, well, great, those 2 vertical lines definitely do project down there, but I don't know how to handle upstairs, because now I'm going to try to be moving around infinitely many points via homotopy. That's bad news bears. So if you do the tilt of a, yeah, okay, so you would recognize that you had the wrong dimension if you had a witness set for this. So if you had a witness set for this, right? And then somebody said, oh yeah, now you're gonna slice with this 2 plane. You're like, nah, I can't slice with 2, right? So if you already have a witness set, you already know the dimension upstairs. And so what you need to do is you just take the cylinder and you replace it by a random hyperplane section of the cylinder. So just Fruit Ninja that whole cylinder with a machete. You're going to get some oblong thing. That's your new variety. That will have the same image. You're just slicing down every fiber simultaneously. So you're cutting down the dimensions of the fiber for every hyperplane you throw in. Okay. So there's some care to be taken about dimension depending on how your parameterization comes about. If it's infinite to 1, you're going to have issues. But for the most part, the idea is fairly simple. You just tilt. Okay. Keep in mind that a feature of this process that isn't being shown here is that almost always when you do this tilting, you lose points. They go off to infinity. Okay. Right. Think about like standard idea of an elliptic curve. Boop. Yeah. Right. So if you tilt this line vertically, 1 point will shoot off to infinity. It's really just a 2-to-1 map onto the x-axis, not a 3, even though the thing that we're projecting from is a degree 3 curve. So that's just a feature. A bunch of things always fly off to infinity whenever you do this process to get a witness set for the image. In particular, via the definition of witness set that I've given you, this doesn't give us a witness set for the image. Right? I don't have the F's. I'm never going to have the F's. Part of this story is that it doesn't really matter. Right? I didn't really ever need the F's. I only needed the F's as a means to the end of being able to move points around. And I can do that upstairs. Okay, and so for that reason, you know, the data type that encodes a witness set for the image here is called a pseudo witness set. And you can think about, okay, well, what exactly is the data I need to give this a definition? That's like, okay, I need something that cuts out the pre-image correctly. I need a subset of coordinates like xi1, xik that I'm going to project down to. And then I'm going to need some linear space in, we'll call this xi, in the xi's, and then I need some s. Right, so you could write that down as like a quadruple and call that a pseudo witness set. And people have done this in the literature. But it's a red herring. It doesn't matter how you kind of encode this rigorously. From an abstract point of view, what you need are isolated points of a linear section and the ability to move them around. That's what a witness set really is. Okay. So this is the story of what's known in the literature as pseudo witness sets. It's what allows you to get your hands on varieties whose equations you don't know. It's really, really powerful. Oh, for example, all your exceptional sets of discriminant show up this way. They're the image of the ramification locus upstairs, which is a locus where solutions have Jacobians which drop rank unexpectedly. So those equations upstairs are easy. Downstairs, I've warned you multiple times to never try. So yeah, this is one way to get witness sets for discriminants and exceptional sets. Pause for questions. Okay, now I'll stop the recording for questions.